So here once more we are looking at the moon. And that's part of the problem because if you look at the civilization of the Earth, it's still a very primitive planet because any advanced civilization wouldn't be stuck to their little fish tank. So now anyone can point a camera at the moon and you can see the static hemisphere, can't really see the far side. Um, but here's the problem. Space exploration is in its infancy, right? And even what we have now is not entirely available to all persons of moderate means. This is not basically anyone can hop on a flight, you know, anywhere in the country. But eventually we're going to get there. That anyone, hopefully anyone of moderate means, will be able to voyage into space. No different than a commercial airline. But the technological level of the Earth is it's not there yet. It's just simply not there yet. And so now, as we discuss the curvature of the Earth, this is a question about a controlled scientific experiment methodology. We're not encouraging, you know, any active experiments, but we're just thought hypothesis. Very blunt and to the point. Based on the different tests, we might get this wrong. If you have two static points at the exact local elevation, what is the at what point do you no longer have convergence to irrefutably prove the curvature of the Earth, accounting for refraction? So we understand that if you have 2 points that are not, probably this is probably not correct, but our understanding is that if they're not sufficiently placed far enough, the atmosphere can refract, causes the light to bend. And if you look at the moon over the horizon, it appears bigger just as it's over the horizon. The atmosphere, Earth has an atmosphere, and the atmospheric conditions can affect the way light travels. This is basic physics. Anyone who actually took a college physics course, even a basic course, they probably did some light refraction experiments, prisms, whatever, light experiments. But if you have two points sufficiently placed apart, what is the minimal distance that you would need to be able to control for any type of atmospheric conditions, atmospheric um, issues, so that the results can be conclusive and controlled for any variation due to the atmosphere. So basically, measurements, a lot of times, this is from geotechnical instrumentation. If we take a distance, meter and shine it at a target, basically we're measuring for deformation. So just making it up. If the number that you're getting, right, it's not always like, if you're getting a reading of 3.7753, the next reading you get is 3.775, and the next reading is 3.7751. It doesn't actually mean that there's actually structural deformation, because basically if you're manually using a distance meter with a laser, there's different human errors, basically the bolt, uh, when you install the distance meter. So basically a lot of experiments using distance meters, extensometers, and inclinometers, it basically, one reading is not literally one reading. Sometimes it takes, you might, for example, take 10 different readings, um, times 5, and you get an average with a limit, basically with a deviation range. So just because one reading shows 5.5 and the other one shows 5.1, doesn't actually mean, so basically there's any actual structural change. So for example, as long as it's within range, for example, just making it up, so like 3.775. 3.775, but you're going to have some deviation. For example, at the last, you're going to have 351, 153, something like that. But it's an average of the readings. So basically, looking at a controlled experiment, is there a way to actually uh, irrefutably prove or disprove the curvature of the Earth, fully accounting for any type of standard deviation by the atmosphere, whether it's like ocean currents, equipment, issues. So we mount a camera on a tripod, um, but we're never going to get the same image twice. You never get the same image twice because um, the way you mount it is not always going to be perfect. So how do you set up a controlled experiment where you can actually collect data that can be converted into useful information in a highly democratic way? So we don't expect NASA, ESA, or other space agents. They're not even bothering to address this question whether the Earth is flat, whether the Earth is spherical. But we believe in democratic science, that everybody should have access to science. It's not something, you have a PhD research paper that, basically there's an elite squad within this, basically the ivory tower of academia. They're the only ones who, do research and stuff like that. We want to make sure that we can democratize science and have a paradigm for real scientific experimentation, for people on the ground here. So how do you set up an experiment?